Welcome back. This learning module is on strings in C, and you'll hear me say now as well as a couple times in the future that strings are really just a special case of arrays in C, which we've already covered in the prior learning module. But I guess it's fair to say they're sufficiently special or sufficiently different than our common use of arrays that it's worth dedicating an entire learning module to and to get additional programming practice with. My goal is for this joke to be funny by the end of this lecture. If it's not funny now, that's okay. And if it's not funny at the end of this lecture, it's not necessarily your fault or a lack of understanding. Maybe it's just a somewhat lame joke. But this is the kind of humor that computer engineering professors find funny. Even for the prior learning module, we actually have been using arrays quite a bit. We were declaring things like names or other blocks of text as these character values. So we would have, for example, in our code, car, my name equals, for example, Joe. And we saw with arrays that this was valid syntax, that as long as the array was initialized at declaration time, it was okay to not actually explicitly say, here is the length of that array. Other than this syntax where we're actually doing double quotes to specify that it's a string versus an array of any other type in C, and there's a little bit of some memory allocation difference as well, strings, quote unquote, aren't really a separate type in C. The second example of a declaration would have been an equally valid, arguably more cumbersome initializer given what we already know about arrays. Again, this initializer is using the double quote syntax to initialize it all at once. But we already saw the syntax for initializing, say, integer or floating point arrays, in which we use the curly braces and we did an initialization kind of on an element by element basis. We declare the data type, the name of the array, the bracket syntax, and then we would just declare as initializer the individual elements for that particular array. And just like for a regular array, you can do this multiple initialization of the values in an array at the time you declare the array, but not afterwards. We tried doing that where we would set that A equals B, if you recall, in that multidimensional array example from the prior learning module. We couldn't do it. It wasn't an assignable type was the warning we received. Same thing is the case because our character arrays are just really a special case of our arrays. So we can declare a character array of size 5 and not initialize it, but when it comes time to initialize it, we can't just assign it an array value. This looks like something that should be valid C. And I understand the frustration with not being able to do that in C. We'll learn how we actually do that in practice, but it's not allowed because that's an array like any other array. And at least in C as a programming language, you can't just be explicitly copying one array to another using the assignment operator. You have to write some loop, or as we saw, have copy functions that allow you to copy blocks of text over. We've actually been using strings all semester long because every time we've used printf, that's involved strings. Let's take a look at this simple case and it allows us to understand a little bit more about the inner workings of strings. This example where we've declared some character, we've done some initialization of a character array for first name, Joe, or what have you. And later on in the code, we've done printf, your name is %s, to indicate that we're printing a string. Your first name is %s, first name. I think an interesting question in terms of understanding our strings as in a special type of array is how does printf as a function know actually where the end of the string actually is? It's just an array of character types, and nowhere in that printf function are we actually passing length information anywhere, right? Nowhere in that function are we saying print out this string and it's actually of length 20. And the answer is kind of interesting, and the answer is something we'll be running into time and time again as we work with strings. The C standard includes a convention that all of these character arrays that are going to correspond to text data, that are going to correspond to strings, end with the special character \0. It's the same as just ASCII value 0, so sometimes you just see it encoded as a 0, but the character is \0. It's the null byte or the null character. Sometimes null is with 2 L's, sometimes with 1 L. It's all referring to the same exact concept. ASCII 0, that special \0 character, or just null. Syntactically, all are actually going to work, but we can always check for our code if the value is equal to 0, the number 0. So as you're looking at documentation or looking at other programs or explanations, and you hear or read the term C string or null terminated string, it's referring to that exact concept. That strings in the C standard to encode text, they are character arrays like any other array, but by convention, they have a 0 at the end of the array. And if you don't, in fact, have a 0 at the end of the array, well, you're going to be like the string that walked into a bar and wasn't null terminated. And the printf function did not know when to end printing that string. That's the joke. Okay, I didn't say it was a great joke, but that's why those functions work. That's why functions like printf work, because they can expect by convention there's going to be that null byte or null character or 0 at the end of every string. The big implication for us, at least to start with, is that when we're defining arrays of that character type for use as text strings, we actually need to have one more byte, one more entry in the array than we think we would otherwise need. It's pretty easy to mess this up. In fact, the example from 2 slides back is actually wrong, where I initialize as an array called car my name as a J, an O, and an E. If I actually did want to initialize a character string with a J, O, and E, I'd actually need to include the space for the null byte as well. And our layout of memory should look like the following, where the first byte is the J, the O, the E, and then there's extra space for that null byte. I still don't have to be explicit with the length of the array, but to encode a text string with 3 characters in it in C, you need 4 cars, not 3. You need the actual text, you need a 0 or a null byte at the very end of it. For better or for worse, this replit environment that we're using kind of papers over some of these details for you. As we saw as we were trying to overflow memory in the prior examples from the previous learning module, there's a lot of zeros kind of initialized in memory. I couldn't get it to crash, even though in my environment on my own machine, I was able to crash it pretty quickly. So since it's initializing the entire memory space for you, you may get away with not correctly null terminating things on occasion, but it's still the right convention. We still need to take advantage of this knowledge to be able to correctly work with strings in our code. This is an important kind of reference slide for when you have to worry about the null byte and when you don't have to directly worry about the null byte. You do have to worry about it, like the example on the previous slide of when you're building up your own string from a sequence of characters kind of manually, either at declaration time or via some loop where you're initializing a string to some values. And if you do so, you do need to make sure that you're including the actual letters you're interested in, but then you're actually also including that null byte at the end, and that you have sufficient space to store it. You also do need to be aware that the null byte exists when you're initializing a character array and you're explicitly saying here is the length of the array. Car, first name of size 4 equals Joe. If I do size 3, that's actually wrong. That's tricky. So a possible workaround or a possible way to not have to worry about it as much is when we're working with string literals, that null byte's going to get automatically included. And all of the functions we're going to be learning about working with strings, including some we've already been using, they all assume there's a null byte there. They all copy over a null byte if we're copying one string to another. You generally don't have to be doing a ton of work of manually inserting null bytes. We're going to do a quick example of that just to show how that would look in practice. The other time you don't really need to worry explicitly about the null byte, the null character, is when you're initializing a string literal like we would normally do so, and you're not explicitly specifying the size of the array. Very similar example to the prior example here on the left. Here we're not specifying the length of the array. C as a standard and the compiler is smart enough to recognize you've declared it with 3 characters to initialize the array. The array length actually needs to be of size 4. So it will do that for you. And that's a nice feature. So we have to be aware that that null byte always is supposed to exist. We sometimes ourselves do have to check for the presence of that null byte. We have to make sure we have enough space for that null byte. But the libraries we use, the functions that are commonly used, do take care of a lot of that for us. The other thing to keep in mind is that because of some of the special nature associated with strings, and I guess also because of how fundamental working with text is with writing programs, there's a larger number of functions in the standard C library for commonly needed string-related functions. This is just a few of them. We have string length, for example. It returns back the length of a particular string. There's string copy, which copies one string to another string. We saw that memcopy function, which is very similar. The main difference is string copy function needs to be aware of that null byte. Otherwise, it's almost an identical function. String cat is my favorite function because I just think of a cat playing with string, but that's short for string concatenate, and so we're concatenating strings. String comp or string compare is also an extremely important function for us and a common function that we're going to use because we don't have an equal operator for strings because they're an arrays, and so we can't have them inside our direct operators like we've seen. But string compare is a comparison between two strings. It's kind of the equivalent of an equal operator for strings. And then there's others. There's quite a few. And having access to the reference for the C standard library functions, it's pretty critical. You pretty much need to have it open while you're working with text data to either remember the interface, to look for examples to the interface for these functions, or just to kind of generate ideas for how you're going to do the text processing you need to do. We can actually replicate all these functions ourselves. They are not inherently that much harder to write than the functions we've already been writing for working with arrays and loops and the like. In practice, though, these are pretty highly optimized pieces of code that actually are probably a little bit beyond our programming skill set, at least as of today. I brought up an example from the open source C standard library implementation for string length. And as part of PP06.1, you're supposed to kind of re-implement string length yourself. We'll do this as part of the lab and not directly in class here. If we look at the quote-unquote standard implementation that is used in the open source systems for string length, well, one thing you may notice right away is, here, I'll make it a little bit larger, is it's not in C code at all. It's written in assembly code. Well, that's one thing. By the way, if you submit this for your assignment, there's something a little fishy going on, and I don't expect you to. But it's actually not even written in C because they're so concerned about the performance of this very critical function. It's written in assembly code, and I can say as someone who writes a lot of assembly code, it's written in pretty advanced assembly code because it's really attempting to get as much parallelism out of the operation as possible. If we were to write it ourselves, we use a single for loop, we check byte by byte by byte by byte. When we get to the null byte, we are done. This is doing multiple bytes at a time in an attempt to optimize how efficiently you can do the string length operation. So those functions exist. I guess one takeaway is that they're very well written. And another takeaway would be, we should be using them whenever possible. So let's do a slightly different programming exercise then, in which we're going to read in a sentence from the user. We'll use this fgetS function that you're going to start to be using more and more in your programs. And let's see we'll call it fun. As we've discussed, fun is a relative term, but what fun can we have with strings with the various string.h functions there for us? I think at around this point, if you've not already gotten to this point, is working on the programming practices, you're really going to have 3 or 4 windows open while doing your programming, right? You're always going to have like the specification window open. For us, that's our README markdown file. You always want to have that handy. You don't want to be blindly just programming without knowing what you're supposed to be programming and working on. You'll have the code itself. Depending on how you like to work, you'll fit it all in one window. You may have it in a few different windows, depending on that's personal preference for how you work on your code. You're going to always want to have like the documentation window for either the library in our case, for the API you may be using for more advanced examples, for like a data format you may be trying to interface with. For us, it's the string function window we would want to have open. And then I would say like the fourth window you'll always want to have open is your Slack or your Discord or Microsoft Teams or what have you for team updates, quick questions. For us, that's Discord for this class. And I hope you're at the point where you're feeling more and more comfortable asking lots of questions. So when I open up example string fun here, it's actually 3 different windows I currently have open, and that's not an accident. We are looking at both the source code window, which is currently empty. I mean, it feels a little sparse. Let's at least put a main here so that we don't get a compile error. That's our one tab that is open. The other tabs that are open are the documentation for the string functions. And then because we're using this fgetS that you may not have that much experience with as of yet, I just wanted to have that document open so we don't struggle or it doesn't look like magic for how we're implementing that particular function. So the spec for this one is a little loose by intention. It is play around with the functions that we have and have fun with it. So, okay, let's read in a sentence from the user using fgetS. That's a slightly difficult function because it deals at least ostensibly with pointers. But what we're doing is we're specifying that we have an array that we're going to be overriding. There's a maximum number of bytes we're going to be reading in. and there's a file stream we're going to be reading in from. For us, that's standard in, and you really should be copy pasting this example that you'll see in your code. We like to use fgetS when we're dealing with text that is more than just a single value, more than just a single word, excuse me. If we were to use scanf, and there's nothing wrong with scanf, of course, it stops at a space. If it receives a space character, it will stop, or any control character like that. Whereas fgetS stops at the \n at the new line and also includes it. So that'll come up a little bit as we're processing data. We have a new line that's actually included. So we need to have an array to declare to store the result of our fgetS call. There are some upper limits of how much text an fgetS call can return. There's a constant defined somewhere that tells you that exact limit. It's larger than 1024, so we can start with that. So let's declare our array, which is going to be a string for us, of size 1024. And let's create a little prompt. Enter in a sentence to have fun with. And the syntax is a little unintuitive, but fgetS, it's the array we're overwriting. It's the maximum number of bytes we're potentially going to read, and it's where we're actually reading from. Standard in is like what scanf is reading. It's from that input shell console window here where we're typing in stuff. A good sanity check is you entered in %s. And let's return back the string we've actually entered in, and let's make sure we spell things correctly. Nothing wrong with hello world. That is certainly a string. And a little interesting there, of course, you entered in hello world. Sounds good. You'll note that it added its own new line character because fgetS also returns that new line character. If I'd wanted to put the string itself in quotes, autocomplete's kind of messing with me here. It's not going to look quite right for that reason because it's going to add a new line before that closing double quote, and that doesn't look quite right. For now, let's keep that as it is. We don't necessarily need the new line, but we have it there. Next thing to potentially do would be, let's mess around with it a little bit. This is fun. I find it fun. Without looking at any function, let's mess around by inserting a null byte earlier. You can always manually do it. Input string of 3 equals 0. That could have also been 0 or null, but 0 as a number is perfectly fine. What's going to happen when we do this? Remember, I talked about as part of the motivation, right? Why does print or how does printf know that it's exactly this many bytes are in my string? It's the null termination. It's that final 0 byte, and that's where it knows to stop. This array is actually of size 1024, but we didn't print hardly nearly that many. We printed until there was actually a 0 that it found. It's going to go byte by byte. When it finds a 0 or that null byte, it's going to be done. It's going to stop printing. So by kind of manually inserting a null byte earlier in my code here, well, what have I done? I have entry 0, 1, 2. Let's do 3, 4. Let's add it at 0, 1, 2, 3, 4. Let's add it at location 5, so at least it's still going to print out a word for hello world. It's going to end the string even though there's some text after that. Because it finds that null byte at that point, it's actually just going to print out hello. We oftentimes don't want to be doing exactly that. I mean, manually changing exact values via updating subscripts in our array directly for strings, but it works. There's a whole bunch of other text. I mean, obviously for this program, I could type in within 1024, hello world, how are you doing? I'm doing just fine. And it's still just going to print out hello because we added that null byte early on, and printf thinks the string is done. And for all intents and purposes, the string is done at that point because we've added a 0 at that point. And if later on we get rid of the 0 and replace it with another character, not to belabor the point too much, it doesn't really matter which one. Let's just add something that we know is just a different character. And then when we do it again, now the string didn't disappear, right? Hello there, how are you doing? We didn't erase that other text. It's still there in the array. And when it comes time to draw it out, you really do need to draw that out to understand what's inside the array. We just replaced it with a 0, and then later on we got rid of that 0. It's added that ampersand. We could have added a space. It doesn't matter. But that text was always there. So when we print it the second time, it is actually still going to be there. So that's fun with messing around with text, and that's fine. Let's take a look at some of the functions that it may make sense for us to kind of quote unquote, play around with in our null terminated byte strings documentation. There are a lot. There isn't any particular order we may be interested in. The one that I think is kind of fundamental is the one that I showed the assembly code for. That is string length. If you're going to use a function, open it up in a new tab. It's going to be an array encoded as a pointer here. Take an array and it's going to return a size t number of bytes. When in doubt, print it out. I would say string length of input string is %d isn't technically the right signifier for a size t output, but it'll work for our purposes. Yeah, it's a little unhappy about that. Extern long, blah, blah, blah. Seems a little unhappy. Let's give it a go. String length of it is 13. We'd have to double check that that's the case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But there's that null byte. What about that null byte? Why isn't that null byte included? Returns the length of the given null terminated byte string, the number of the characters in a character array whose first element is pointed to by string, and not including the first null character. So that's why it returns 13 and not 14. Good to know. That's probably what we would want in using this string length function. And why do we want to have the string length? Just call it length just to store it so we don't have to keep calling it later. Maybe do it beforehand. Remember, our scoping rules allow us to put variable declarations wherever we want. This is for us to have fun with. We're not meant to use this as best practice necessarily. This should return the same result. Good to go. It's very useful to have that length parameter, right? We're typing in an arbitrary amount of text, and a lot of your programming practices are with some arbitrary amount of text. In past examples, we did pound-defined length of 50, and that's how we knew the length was going to be 50. For this string, it's based on how much someone has typed in. When they hit the enter key, fgetS returns. That's the length of the string. So calling string length, or implementing it yourself, because we know it's something less than 1024, so we could write a for loop for it. But having that string length is very useful now when we want to do for loops to maybe process the string. So this becomes our very common programming pattern. I equals 0, I less than len, or you can explicitly just call string length at that point again. But I less than len, I plus plus. Do something. And that something we would do would be on input string of I. I don't know what that something is yet, but we'll do something on that input string of I. Now we're back to our what are the fun things we can do. Well, we can check if a character is alphanumeric. That sounds moderately fun. We can check if it is digits, uppercase letters, lowercase letters, and returns a non-zero value if it's an alphanumeric character, 0 otherwise. Kind of curious what that result looks like, so let's just print it out. When in doubt, print it out. I don't know. Let's give it a little header here. That's wrong. I'm not trying to print out the actual character. I'm trying to print out is alphanumeric, is alnum of an input character. So printf, let's call it is alnum test, something like that. And let's put a new line at the end. Now we're having fun. Expected, semicolon, after expression, printf is alnum, input string. Oh, well, I just missed a semicolon. I thought it was going to be a more interesting bug. Hello world. It says non-zero if not alphanumeric. That's okay for our true false, right? False is non-zero, false is 0, true is non-zero. I'd be curious to see in the implementation why it's returning 8 for hello and WORLD. But it is. You may be wondering, why are there 2 zeros at the end? Well, there's the exclamation mark, and then there's still that new line character. We want to get rid of that new line character, because it is annoying me. How could we do it? Now it's not fun. Now it's serious stuff. How about get rid of the final character it's a new line and we don't want it. We know how to get rid of the fifth character, or sixth, or fifth from 0 from that location, offset 5. How do we get rid of the last one? We know the length of the array, or at least we can calculate the length of the array. So it's not input string of 5 is equal to 0. We can take a look at input string of string length of input string, or we could have declared that length variable or used that length variable. And the length, let's say, was 13. We'd want to get the 13th element, that last new line, and set it to 0. And that last one, it would be at offset 12, right? Because we always start with 0. It's okay if that doesn't make just perfect sense right this second. String length returns the number of characters because it doesn't include the byte. There's 13 characters in hello world with an exclamation mark, plus the new line character. We want to get rid of that 13th one. The 13th one is at offset 12. So string length returns 13. We then want offset of 1 from that. That's why we see the string length of input string -1 setting that to 0. We type that in. It's going to print a little bit better now because we just got rid of that new line. It looks a little bit better. It's of length 12 now. And string length does now return 12 because we've changed the length of the string by adding an extra null byte a little bit earlier on, overriding that new line character that we had. Okay, so we printed out the, let's add an extra little gap here so we can kind of like see things a little bit more clearly. We've done our is alpha numeric test. What else can we do for fun? We have plenty of time. Is alpha, that sounds like if it's alphabetic, if it's lowercase, is it uppercase, is it digit? Those are kind of really subsets. Is control, is graphical, is space. How about two lower or two upper? That sounds promising. Two lower has a very similar interface to our is alphanumeric, takes an input character, converts the given character to lowercase according to the character conversion rules. Okay, so capital A becomes lowercase a. Hey, let's do it. To lower test, we can either actually change the value of the string, that would be perfectly fine, and that may be what you want to do, or we can just print out the lowercase version of it. Really depends on what this, the specification for the problem requires. There's no one, one's not more correct than the other. Sometimes we just want to print it lowercase. Other times we actually want to convert it. In this case, we could do either. Let's just print it for now. So that would be %C and then to lower of input string of I. No errors there. We also could have, I'll just leave it as a comment inside the loop. We also could have done just input string of I equals to lower of input string of I. That would make the whole thing lowercase. Again, we're having fun with strings. There isn't really one correct thing to do here. There's only, well, let's do capital W for hello world. It should return hello world now as lowercase. If we had actually gone through and converted the whole string to lowercase, we could have just printed it off with one printf statement, right? With printf %s again, and then it would actually be lowercase. We can make it kind of look more hardcore and say if I mod 2 equals 1, if it's odd, print it lowercase. Okay. Otherwise, print it uppercase. To lower, corresponding thing is to upper. And now, no matter how we entered it, hello world now looks kind of annoying, for that reason. So every other thing is alternating based on the index. If it's odd or even. If it's an even index, it should be uppercase always. If it's an odd index, it should be lowercase only here. There's other things, so we could do. I think given those is tests, there was is space. I think is a useful one. We haven't changed the string. We just were printing it differently, so we could do is space. It can be very useful to know whether or not you have a space in your string or not. You may have already been playing with that function. Where here the numbers aren't the same, but it doesn't really matter. It's still returning back That actually is a little interesting. It's returning back 8192 when we're actually getting a space. So we really want to, instead of printing out the result of is space, we want to then say if is space of input string of I is not equal 0, I would just print out a 1 instead. So we're still calling the is space function, but our printout looks a little bit better. Now we got our kind of binary looking pattern matching up with where the spaces are in the actual sentence. We talked about the relational operators, by the way, and that would allow us to do that all in one if we wanted to. Printf %d, and the actual integer we're printing out is whether or not it's equal to 0. We talked about how we don't usually do the assignment of a relational operator to a variable or to use it as an expression like that, but that's kind of what that 1-0 logic was doing for us, right? We're printing whether or not it was equal to 0. It's okay to get these kind of backwards, but that actually worked out pretty well. It's the same exact logic. If it's 1, if they're equal, print 0. If they're 1, if they're not equal, print 1. The same exact logic with the if statement that we had there. What else can we do here? Let's take a look at some of our other string functions here. That's 2 lower, 2 upper. Don't really like the A to F and A to I. There's better ways of doing that we'll learn later on. String copy can be pretty useful. String dupe for string duplicate is also pretty useful. Let's take a look at string dupe first. Returns a pointer to a null terminated byte string, which is a duplicate of the string pointed to by source. We haven't really learned pointers yet. I'd rather us use arrays instead, at least for right now. So we can look at string copy. String copy takes 2 strings as input. One is a destination string, the other one is the input string, and it copies the null terminated byte string pointed to by source, including the null byte to the character array whose first element is pointed to by destination. That's a pretty common one. We'll declare a car copy, and we actually don't know how large to make it if we're statically allocating it. Just to be on the safe side, for better or for worse, we really have to allocate that entire buffer size. So we have our function string copy, and again, having these tabs open is so common. I have it open right here. Destination comes first and then source, or better or for worse. Copy, same with the mem copy call though, I guess. Copy and input string. And then I would probably just to test it, copy is and the actual then value of copy we're printing. That should be hello world without looking so silly, right? Because we didn't actually change the value of hello world. So while we were printing out hello world, string copy test, I guess for those other tests we were doing a new line first. But actually this looks just fine. Hello world, how are you, spelled incorrectly. That's a pretty fun one. We got a bunch of other ones. In the interest of time, we can only do so many. String comp is pretty important. Let's open that one up. Compares two null terminated byte strings lexigraphically. That's a 10-cent word. It does some sort of comparison. For our purposes, we really care whether they are equal to each other or not. Left-hand side and right-hand side, so maybe the order doesn't matter that much. Let's try a string comp test or string compare test. And let's create some tests. Let's create 4 tests. And again, we can declare our strings of multiple length here. Let's see if we can do this a little bit simpler without doing multidimensional data as of yet. Let's just do a manual comparison against a hard-coded string. And let's print out the result of doing a string comp of, doesn't really matter which one is which, hello world, how are you, with our actual input string. Or we could have done the copy as well. takes the result of that string comp function and is just going to print it out as a zero or non-zero value. I type in hello world, how are you? I get a string comp result of 0, meaning they are equal. So you're doing string comps and you're checking if they're equal. Instead, hello world, how art thou? We get a result of -15. And I just think about what -15 means in the context of the specification for string comparison. But at least it's not 0, meaning the strings are not the same. That's a very important thing to use when doing some text processing here. Do we have any other functions that are interesting? I mean, they're all interesting to me. Mem character finds the first occurrence of the character in the initial count bytes, each interpreted of an unsigned car, of the object pointed to by pointer. Behavior is undefined. If access occurs beyond the end of the array search, well, we will never do that. Reads the bytes sequentially and stops as soon as the matching byte is found. So it allows us to look for something in our string. This is pretty ugly. Let's copy paste the prototype, although we're going to have to modify it a little bit. Here's our memcar test. Well, what kind of thing would we maybe want to look for in our code? This would probably have to be a pointer. So this would be matching word, and it's the result of the memcar function of the array we're testing. The character, let's look for a space character. I think it's just that because it's a single character. And how many do we want to look for the match? Well, we know there's only length valid characters here in it. We could check all 1024 of buffer size, but we really don't need to. And of course, we'd have to print out match is this. What did we get back as a result? Let's put it in quotes again to kind of keep it consistent with the other examples we have here. Hello world, this is growing tiresome. Okay. And it's kind of interesting what happened there, right? We did match the string when it finds the first space, and it's basically returning you via some pointer magic the string with that first space being matched. We probably could call it again, and let's do so. The second time around, not calling it on input string, but calling it on itself. It actually gives the same result. Oh, but because it's that space is actually now the first character. That's returning the location in the array that is already corresponding to the first one. If we actually wanted to go to the next element in the array, I can actually just say plus plus. Go to the next location. Start at the W there. That should give us the second part of the string. Let's do a more reasonable sentence. First time we called it, it returned this is a reasonable sentence. Next time it returns is a reasonable sentence. If we want to parse out the words in a sentence, doing successive memcars would work for us. And there's also something fairly similar called string car. Excuse me, that's the one we did. We did string car. We can do string as well. Finds the first occurrence of the null terminated byte string pointed to by substring, and the null. This is very formal sounding. It's the same thing except it's matching substrings as opposed to just individual strings. Now I called memcar and not string car. What is the difference? I don't think there's a difference. That's not the one I said I was going to do. Let's make sure that string car gives us the same result, and then we can look at string, and then we can call it done. Just a quick refactor here. We'll keep the original example just to confirm they're the same. String car, the only difference I see it now is in the definition. We don't need to pass length information. Why do we not need to pass length information? Because it's a string. It's a null terminated string. We can figure the function can figure out the length. It's actually not the difference isn't terribly interesting, but they're different. But for our purposes, it returns the same exact result. And then finally, we have our string test. Input string. Let's look for the word world, I guess. Hello world, we are done for today. Hello world, we are done for today. Now when we look for the word match of the word world, we get the subset of that string that starts with the word world. So that can also be very powerful if we're looking for a very particular string inside our sentence. This is probably a pretty good stopping point for us. We covered a lot of quote unquote fun there with regards to the various string.h functions. They use a lot of that pointer syntax that we have not covered yet. I want us to be able to become sufficiently adept in using these functions, and then we'll learn a lot more about why the pointers are working as they do in practice. There's a real connection between arrays and pointers and strings and pointers. But for our purposes now, for this set of programming practices, we can just become pretty good at understanding how to use these functions, following the examples I've just provided or looking at the documentation. And you can write some pretty powerful code, even if we don't really understand all the ins and outs of why the pointers are working the way they are. We have another video on this topic where we'll go through a slightly more complicated individual example here. I try to apply the problem-solving process to string handling, and I think that'll tie in directly to the programming practice you have for PP06, which is one of the tougher ones you'll be working on this semester. Okay, good luck, and I'll see you in the next one.